Greetings, math fans. All right, so today is we're going to talk about linear and angular velocity. Okay, so even before we get into the equations for linear and angular velocity, let's just talk a little bit about what this really means. Okay. I can't really describe it too well in class. I would actually do a nice little demonstration here. But if this is me in the middle, and I have a string, okay, and I have, I don't know, let's put a star on that. And I took that star and I started going around and around and around and around and around. Okay, we have two kinds of velocities. All right, first of all, that when I'm on this line here and I actually measure the speed, how fast I'm going, that's really the linear velocity. Okay, and you can measure that speed as in like miles per hour or feet per second. Okay, that's linear velocity. If somebody clocked you going around the circle, how fast you going around that track. Okay, angular velocity is just what it says is using that angle. How fast is the angle changing? Okay, how fast am I spinning around? And that might be something like a revolution per second. Okay, so that's actually, if I'm spinning around and just turning around, how fast is it going to take me to make one revolution? Okay, or sometimes you think of a rotation per second. And actually, when we use angular velocity, we're going to convert it into radians, but I just want you guys to understand the basics behind it. So it's like a revolution per second or a rotation per second. Now, an interesting thing too here is what happens if I pull this star in? Okay? What's going to happen is, do you agree I'm going to be still going around? I'm going to be still turning the same speed, right? So my angular velocity is actually going to be the same, but what's going to happen with my linear velocity? Isn't it going to be slower? Because I'm kind of pulling in a little bit, and this is not going quite as fast as I pull it in. And then if I went and I got bigger, right, a bigger line like that, isn't that going faster and faster and faster? I mean, even as I take my pen and I draw around it, right, let me use a different color here. If I'm here, right, and it takes me 1 second to go around, how far have I traveled? Well, if you measure it, it's maybe 1 inch, 2 inch, 3, maybe 6 inches to go one time around. Well, if I do the next one, this next circle, and I do the same speed to go around, if it takes me 3 seconds to go around, obviously I'm going a lot farther, right, in distance for arc length. So that linear velocity is faster. And then even the one above here, right, if I go the same speed around, I'm going a lot farther just to get around in that same amount of time. And so my linear velocity is changing, but my angular velocity is actually staying the same. All right. Think of it as also ice skating. When you do crack the whip, okay, you grab somebody and the person in the middle, right? And let me use a different color here again. Okay, the person in the middle is just slowly spinning around. They're really not going very fast. They're not getting dizzy. And then as you go farther out, they're going faster. And as you go farther, and what happens to that person that's way far out? They're the ones that are cruising really fast around, right? And if you let that person go, they're going to go flying. But if you only had two people here and you let them go, they're not going to go too far. So it's kind of what the crack the whip is. It's the linear velocity is really fast, but they're all spinning around the same. They're rotating around the same amount of times per second. Okay, it's just the outer ones are going really fast and the inner ones are going really slowly. Okay, so that's kind of the idea about linear and angular velocity. All right, so let's come up with some formulas here now. Let's talk about linear velocity first. All right, do you guys remember our nice little friendly formula is D is equal to RT. Distance equals rate times time. I call it the dirt formula. Okay, so what we're going to do is we're going to kind of apply this to going around in a circle for linear velocity. And we're going to say distance is the same thing as S, which is our arc length. All right, and our rate, we're going to call that our velocity. Okay, and that's always going to be the letter V. Okay, so we've got that, and that's our it's our rate. I mean, we know that R is our rate. So we can rewrite this as S equals V times T. And so V is our linear velocity, how fast we're going around. So we can say the linear velocity is the arc length divided by the time. Okay, that is a really important formula. In fact, I'll put it in red. Got a couple formulas you got to memorize here, and that's a super important formula. The velocity is basically the distance or the position over time. It's pretty easy to remember that, right? That is position, or really arc length, or like we can think of it as, if think of it as like feet, right? That's how many, the arc length is how many feet. Feet per second, or miles per hour. I talked about that before. Okay, and of course that's time. Okay, so that's a pretty important formula. The next one is going to be angular velocity. All right, angular velocity, as I talked about before, that's how many rotations you have per minute or per hour or per second. All right, and we're going to use a nice little fancy letter here. This is called omega. That's actually a small omega, and I believe a capital omega looks like that. All right, but we're not going to use that. We're going to use a little omega. And omega, remember, we talked about revolutions per second. So omega is going to be theta over t, because theta is your angle. But the only thing, the deal here, and this is super important, I'm going to put a couple of stars next to it. Theta must be in radians. It's very important. Theta's got to be in radians in order to use that. All right, super important. So, I mean, it's good to recognize it. If I give you something in revolutions per second, that means you're just going to change it from revolutions, or I could also give it to you as rotations per second. Okay, if you're given either one of those two, you better convert that to radians. Well, how do you convert it to radians? Well, isn't the conversion 2 pi radians per revolution or per rotation? Okay, so that's going to be the unit of conversion to convert it into radians. That's really critical. Okay, super important. And all right, so let's kind of talk a little bit about kind of developing a couple formulas here. We did an example, showed you at the beginning about what angular and linear velocity is. So linear velocity, let's actually write that out here. V equals S over T, and omega equals theta over T. Okay? And just to kind of talk a little about, right, we already talked about S. Isn't S equals R theta? Okay? And so basically the arc length is based on the radius. Right? And that, if we come up with another formula here, instead of saying V equals S over T, we're going to substitute that in for S. So V equals R theta over T. Okay? And those are related to, because we have omega is equal to theta over T, and I can just substitute that in. So V is actually equal to R times omega. Huge formula. Going to put that in red also. Huge formula. And let's talk a little bit about what that means. When I showed you the picture of taking the string with a little star at the end of it and spinning it around, do you guys agree as the radius got bigger, what happened to that? What happened to the velocity, the linear velocity? Didn't it get faster and faster? So in other words, you're spinning around at the same rate, and you're letting go of that string farther and farther out. That string is still rotating the same amount of times per second, But the speed of it now, it's getting really huge, right? It's like crack the whip. So linear velocity is based really on the radius. Okay, it's the radius times the angular velocity. All right. So that's again, it's really important. That's just a super important formula there to recognize. All right. A lot of times, I'm going to write this out here. Many times, angular velocity is given in terms of revolutions per time. And I know I mentioned this, but this is just so important. Many times angular velocity is given in terms of revolutions per time, because really it's so rare that you're going to see anything where they say, oh yeah, I'm spinning around at 5 radians per second. Okay, that really doesn't happen. You don't see that. But you say, oh, I'm spinning around at 100 revolutions per minute, or 200 RPMs, right? RPM, revolution per minute. And that's fine. So it's many times you're given it to revolutions per time, and you must convert. So you recognize it. This is just a recognition thing. Okay, that is your angular velocity, but you got to convert that to radians per time. Okay, very, very important. All right, so keep just be aware of that. All right, so let's do a nice friendly example here. You guys may not even remember or know even what it is, but hopefully you do. Okay, so an example is you have a record album. And maybe your father or your grandfather or great-grandfather, I don't know, somebody's got a record album, and the record's spinning around. And you've heard maybe of a record is a 33 RPM record. You have 33 RPMs, you had a 45, and you actually had 78, so that's before my time. But when I was a kid, I used to buy 33 RPM records because you could buy a single song at a time, and I like that. Anyway, 33 RPM, revolutions per minute. All right. The diameter of a record was about 12 inches. And the question is find the linear velocity when the needle first hits the record. First hits the record. So this is kind of what it looks like. Here's your record, and you have a little arm for the record player, and it first touches down, it hits the record right at the edge like that. And the record is spinning around and around and around at 33 revolutions per minute. So what I tell you, when you see revolutions per minute, what are you going to think of right away? You're going to think of angular velocity. So you're going to think of omega. But of course, you have to remember omega is going to be in, right? It's not in revolutions per minute. It's in radians per minute. Got to remember that, okay? And, because our equation, right, is theta angle over time, okay? And so that's got to be converted into radians. All right, so let's do that. Well, I guess we got to write out the whole equation. We're looking for linear velocity. So linear velocity, V is equal to R times omega. Okay, so what I'm going to do is I can say V is equal to R. Well, that's pretty easy. That's not 12 inches, but it's half of that. So it's 6 inches. So 6 inches. And then omega is going to be, well, let's try it out here, 33 revolutions per minute. Okay, we're going to use a little dimensional analysis here, and we're going to convert revolutions to radians. So it's going to be 2 pi radians per revolution. So the revolutions cancel out, and we actually have, and radians are really unitless. Remember I told you that? So we really have inches per minute. And that comes out to be 1244 inches per minute. Okay, that's the, and then that's a unit. That's fine. I could ask you feet per second. It all depends on what I ask for, but it's a linear velocity because it's distance, which is inches, over time, minutes. All right. What happens if you, instead of it dropping in the middle, let's say it drops. Let me kind of redraw this here. Here's your record again. Let's say it drops in the middle of the, like somewhere over here in the record. Okay, because you're playing a certain song. That's what you had to do with the record. If you want to play a certain song, they had little gaps in there, and you would put it on the song you wanted. But let's say if it drops in the middle of the record or close to the middle of the record, instead of being 6 inches, you can drop 3 inches. So R is equal to 3 because you're kind of cutting the record down. Here's what the record is, and that's like a 3-inch radius. Okay, so we're going to do the same thing. Velocity equals 3 inches times 33 revolutions per minute times 2 pi radians per revolution. And if you multiply all that out, you're going to get 622 inches per minute. So that's in the middle of the record, okay, which kind of makes sense. You're cutting it in half, right? And the whole record was 1,244 inches per minute. So it's going half the speed because we're halfway into the record. Okay, now this is just a little weird. I mean, I don't put it on the video, and I like to talk about this in class. But when you think about it, a record, right? As you travel closer and closer into the record, do you guys agree that the linear velocity slows down, right? Just like crack the whip. If you keep going farther and farther out, that goes a lot faster. But as you go farther in, it is a lot slower. And what they had to do is when they were actually making the records, the music has to be spaced farther apart on the records on the outer part. Okay, this outer ring, the music had to be spaced farther apart than the inner ring, because otherwise it would sound kind of funny. You would have fast music on the outside and slow music on the inside, but they actually had to compensate for that when they actually churned out the records. Okay, so that's just kind of an interesting thing. All right, so that's a record problem. Let's do a different problem here. Okay, so let's talk about clocks. Good old clock problems. Okay, first of all, I want you to, the first thing is find the angular velocity for the minute hand of a clock. So find the angular velocity for the minute hand of the clock. Okay, so angular velocity, well, we know that's omega equals theta over t. Okay, and angular velocity, what we're going to do is we're going to say, well, we could say, well, it's 360 degrees around, but just think about it. I'm going around the clock, so what's theta going to be? Well, theta is going to be 2 pi. I mean, I'm just going to convert it right away into radians. Why do degrees? We know theta is 2 pi. So it's 2 pi over 60 minutes. So that's equal to pi radians over 30 minutes. Or we can say it's 0.1047 radians per minute. Okay? Oops. There's the decimal there. So that is the angular velocity. It's 0.1047 radians per minute. Okay? It's not too bad. And, of course, if I ask you for revolutions per minute, you could just, right, isn't one revolution is 2 pi radians, and you could just do the conversion. You could actually multiply that by, let's just kind of show it, pi radians per 30 minutes, and we could say it's 2 pi radians per 1 revolution. So that would be converting it into revolutions per minute. Okay, you can multiply that out. In fact, so what do you get here, right? That cancels out, and you get 1 over 60 revolutions per minute, which makes sense. 1/60th of a revolution for every minute, because in 60 minutes, wouldn't you have 1 revolution, right? If I multiply this by 60 minutes, which is 1 hour, I would get 1 revolution, which of course is 1 hour. Is 60 minutes is 1 time around the clock. Okay, so that's the first thing I'm looking for. But really, this guy right here is what I was looking for omega, because of course it is in radians per minute for this one. Okay, so the second question I want to ask you guys is, what's the linear velocity? Well, what do I need to give you in order to do that? I actually have to give you the radius of the clock. So I'm going to tell you it's a 3-foot radius clock. Okay. And well, I think I really want to give it to you as a diameter. So 3-foot diameter clock. That's usually the way it's measured. So then, of course, you have 1.5 feet equals the radius. Okay, so the radius is 1.5 feet. So that's actually pretty easy, right? Isn't it just V is equal to R, which is 1.5 feet, times omega, which is, and again, you couldn't use this bottom one. You couldn't use this 1/60th because that's not in radians. You got to use this guy right here. So times pi over pi radians per 30 minutes. Because again, radians is unitless. So what you wind up is feet per minute. And that gives you 0.157 feet per minute. Okay? Okay, let's keep going. I'm going to erase this here now. Let's see, how about the distance traveled for the end distance travel of the minute hand in 15 minutes. Of course, it's still a 3-foot diameter clock. All right, so that's actually pretty easy too. In fact, we don't really need to know a lot of stuff here. What we need to do is, if I said the distance traveled, math fans, I'm looking for the arc length. Okay, so you got to kind of put things together, right? You got to know if it's linear velocity, angular velocity. Am I looking for arc length? Distance traveled is arc length. So S equals R theta. Well, S equals R, which is 1.5. And we'll put the units there, 1.5 feet. And theta needs to be in radians. So this is the deal, though. We're only going 15 minutes. So isn't that, let's kind of do it this way here. Isn't it 2 pi times, and what's 15 minutes? Isn't it 15 minutes over 60? It's like the percentage. So 15 over 60, isn't that like 1/4 of an hour? So you can multiply by 1/4 or 15 over 60. It's the same thing. But that is, that's going to give you, since it's, right, 2 pi is basically radians, so it has unitless, and this is just a fraction that has no units at all. And of course, that's giving you your answer. So S comes out to be 2.36 feet. All right, that's how far it's going to travel in 15 minutes. Okay, how about the angular velocity of the hour hand? Well, that's going to be pretty slow. Do you guys agree the angular velocity of the minute hand, it goes, pretty fast, right? It ticks around, it goes pretty fast. And the angular velocity of an hour hand, that moves really slowly because, hours take a long time. It takes 12 hours to get all the way around, as opposed to 60 minutes, 1 hour to get all the way around for the minute hand. So again, we're going to say omega equals theta over t. And theta is, again, going all the way around, is 2 pi. But the time is 12 hours. So if I'm just looking at that, it's pi over 6 radians per hour. Okay, so that actually, that's radians per hour. What happens if I ask you how many minutes? Well, that's pretty easy, isn't it? Pi over 6 radians per hour times 1 hour per 60 minutes. And that gives you pi over 360 radians per minute. Okay, it's pretty slow, right? And you know, again, that's our angular velocity, and that's with radians. If I asked you to convert that into how many revolutions per minute, well, you would just say pi over 360 times, let's put our units, radians per minute, and I'm going to convert that into revolutions. So it's 2 pi radians per 1 revolution. So the radians cancel, and we have revolutions per minute. Of course, the pi is going to cancel, and we have 1 over 720 revolutions per minute. Okay, that's really, really slow. Every minute's going to go 1/720th of a revolution. So that's why you're going to say 720. And what's 720? Isn't 720 divided by 60? It's 12 hours. Well, of course, that's what it is. So every minute's going to go 1/720th of a revolution. And if I multiply that by 720, which is 12 hours, it's 1 revolution. Okay? So that is another way to look at angular velocity. But just remember, what I asked for. But the deal is, whatever the input is and whatever the output is, that's got to be in radians. All right? It's got to be in radians, not revolutions, but in radians. And that's the output and input of that equation. But a lot of times you're not really asked for the radians. You may be, but you're usually a lot of times asked for how many revolutions. All right. So let us do one more formula here, and then we're going to. I have one more problem I want to do with you. So this last formula is to connect arc length, angular velocity, time, and radius together. Okay, so kind of pay attention here. Since omega equals theta over t, then we can say, if I cross multiply here, I can say theta equals omega t, and S equals r theta. Okay, so if you can see what I'm going to do here, I'm going to substitute that guy right into there, and I get arc length equals, and I'm going to put it in a certain way here. Well, I'll write it the way, so it's r omega t. And just kind of an easy way to, if I rewrite it, I don't care how you memorize it, but you get S equals omega tr. And I look at that as S equals water. Okay, there's no A, because the A goes on your paper. Ooh, pretty clever, right? Yeah, all right, okay. But that's just a good formula to know here, that the arc length is the angular velocity times time times rate. Okay? All right, so this problem is actually out of your book. This is problem number 45 out of your book. And what they do is they said, for problem 45, it says a railroad track is laid along an arc of circle of a radius 1,800 feet. So this is kind of what the picture looks like. It's 1,800 feet is your radius. Okay, not rate. In fact, maybe I'll just get rid of that R here. That's your radius. And here's your track going around. That's your railroad track. All right, so railroad track is laid across along an arc of radius of 1,800 feet. The circular part of the track subtends a central angle of 40 degrees. That just means this is 40 degrees here. How long in seconds will it take a point on the front of the train traveling at 30 miles per hour to go around this portion of the track? So this guy is right here, and he's cruising around the track. And I want to know how long it's going to take him to go around that track the track again is a radius of 1,800 feet. It's 40 degrees, and he's traveling at 30 miles per hour. And I want to know how long he's going to take to go around. So I want you guys to think a little bit, what is given here? All right. Well, first of all, don't you guys agree that, look at the wording, miles per hour. Oh, that's got to be linear velocity. So v equals 30 miles per hour. Okay? And we're given a couple different things here. Well, actually, I need to find out how long it's going to take the train to travel around that section. So I'm looking for time. So let's just look. That's an important thing. So I'm looking for time. Well, do you guys agree? Let's look at what equation we have. We have velocity equals s over t. That's one of our equations that we learned. All right, that was one of the significant ones that I definitely highlighted here. Okay, and in fact, it was the first one that I highlighted. All right. So what I'm going to do is let's just kind of plug things in, and we know it's 30 miles per hour, and do I know my arc length? Okay. Well, yeah, I can get my arc length. Isn't s equal to r theta? Okay, well, sounds good to me. S equals r, which is 1,800, and theta is 40 degrees. Can't just use 40 degrees, though. It's got to be in radians. So we're going to say pi over 180 degrees. So pi radians per 180 degrees. And so we're going to get S is equal to 400 pi, and that's feet. Okay, that's S. So we have S, and let me highlight these guys here. We have S, and we have V. So if I solve for this guy here, right, isn't that just saying, here if I cross multiply, I get V times T equals S, or T equals S over V. And so when I plug everything in, I get S, which is 400 pi feet per velocity is 30. Oh, okay, so now I got a problem here, right? And that's something important. I've got to have it in the same units. So I'm going to convert, it's easier to convert miles to feet than it is feet to miles. Because feet to miles, you use some nasty decimal. So let's convert 30 miles per hour. Let's just do this conversion. 30 miles per hour. And I want to convert it to, we're going to do feet per second. Okay, and I guess I should be a little more specific about it in the problem here, because you're not going to really know what to do. But I'll be specific. I'll say if I convert that to feet per second, well, that's going to be 1 mile is 5,280 feet. And I would give you that conversion. I would never expect you to memorize that. Okay, so that gives me feet on top, feet per hour. And then, well, you can do it kind of the long way here. You can say, well, 1 hour per 60 minutes, and 1 minute per 60 seconds. Okay, so your V, 30 miles per hour, turns out to be 44 feet per second. Okay? So now what I'm going to do is I have feet. I'm going to put this in the bottom here. So it's 44 feet per second. And what happens is the seconds go to the top of the fraction, right? And so if I divide that out, I get, I'm running out of room here. I'm just going to cursor down just a little bit. I get T equals 400 pi over 44, which we have there, and then that's equal to 100 pi over 11, and that's, of course, seconds. You don't really leave it like that. It's too messy, and if you divide that out, you get 29 seconds. And that's your final answer. Okay, the time is 29 seconds. So you see how we kind of related some stuff together, and you got to obviously have the right units, but you got to know the formulas, and you got to recognize if I have feet per second, miles per hour, that's linear velocity. If I have radians per second, or if I have revolutions per second, that is your angular velocity. And then always remember, especially for angular velocity, you got to convert it into radians per second when it's input, or when it comes out, it's always in radians per second or radians per something. Okay, so that's it for angular and linear velocity. It's not necessarily super easy, but you got to memorize a couple formulas and some conversions, and then you're good to go. All right, that's it, math fans. You have a great day. Adios. Goodbye.